Okay, well, I'm Federico Sestito, a postdoc fellow at the University of Victoria, and I work mainly with Kim Van. And today I'm going to present a chemo-dynamical investigation of the oldest and most metal-poor stars in the bulge with GRACES. And this is a project within the Pristine Inner Galaxy survey. And the project has been done in collaboration with not only Kim Van, but also Anka Arensen, which is the PI of PIGS. And you should also go and see the poster. But also with David Aguado, which is doing a similar work, but with US data. So I think Elsa already convinced you why and where and how we can study the oldest and most metal-poor star. And here's a brief summary. So many simulations confirm and agree that there are three main regions in which we can find the oldest and most metal-poor star. And these regions are the inner parts of a galaxy, the satellites, and the halo. And these three regions are very informative on the chemical evolution of these three different regions. And the Pristine survey with its calcium Machenke filter is very efficient in finding this metal-poor star. And it has been shown that we have an efficiency of 23% of recovering extreme metal-poor star, so photospectroscopic metallicity below -3, in which you should also have, we should also have photometric metallicity below -3, and this is much higher than previous surveys, such as, for instance, the HNK survey. And this is the field of view, the footprint of the Pristine and the PIGS surveys. So while the Pristine is scanning the sky towards the halo, the PIGS is concentrating the efforts on the bulge and the Sagittarius dwarf spheroidal, covering up to 300 square degrees. And this is where I will focus today. So for the PIGS survey, a low medium resolution spectroscopic follow-up has been done at the AAT telescope using both the blue and the red arm with these two resolution, collecting up to 12,000 spectra. And this is, again, the footprint in galactic coordinates. And the result is that the PIGS is very efficient in finding very metal-poor star, as you can see here from this histogram, in which we report 4 different surveys, and the PIGS is really finding new, very metal-poor, but also metal-poor star compared to other surveys. Now I want to move towards the high-resolution analysis. So for this work, I'm using the GRACES, and GRACES stands for Gemini Remote Access to CFHT Espadon Spectrograph. And it combines the large collecting area of the Gemini North with a high resolving power and efficiency of espadons. And this is achieved through a 270-meter fiber that goes from Gemini North on the right to the left, which is the CFHT, through this conduit here. And in the middle, there is jump paths there here. And yeah, for this work, we did select 20 very metal-poor star from PIGS with medium resolution spectroscopy of below -2.5 and bright enough to be observed with GRACES at Gemini. And at the end, we end up with only 17 very metal-poor star due to the poor signal-to-noise ratio of 3 stars. And here you can see the field of view of our sample. So now we have Gaia EDR3 data, so we can compute precise distances and also orbits. And here I'm showing the 4 main orbital parameters, which are the apocenter, the pericenter, and the eccentricity, but also the maximum excursion from the plane, the Z max. And we did find 4 main kinematical subgroups, which are the bulge, so stars that are really confined within the 3.5 kpc from the galactic center, a planar subgroup which have a Z max below 3.5 kpc, but an apocenter which can go beyond the sun. And then the inner and outer halo groups, which have a difference between each other by their apocenter. But both of them have a Z max greater than 3.5 kpc. And we did find that the majority, all of the stars have a high eccentricity, and they are somehow compatible with previous bulge studies, such as the one from Lucy 2022 from the COMS survey, in which they also find very similar kinematics as us. Now going to the chemistry. So here I'm showing 3 alpha elements such as magnesium, calcium, and titanium, and also an odd element which is sodium. Overplotted, there is also a compilation from the bulge literature with the crosses, and then a compilation from the halo from Kelty 2021, in which they observed 30-ish halo star with graces. As you can see, the majority of the star in our sample looks like the halo, and this is already a sort of take-home messages that maybe the bulge stars, the stars that are in the inner region of the galaxy, they are just very similar to the halo. So they came from the same building blocks, or yeah, something similar. We should not find the striking difference between the halo and the bulge. But then there is also a population with very low magnesium, which are mainly the inner halo stars, and I will speak about this after. But also looking at the barium distribution, they do look like the halo again. So the majority are within this blob here and this blob here. The exception are these 2 stars, which are carbon enhanced, which means that the barium is coming from S-process yields from AGB, from maybe these 2 stars were in a binary system, and the AGB contributes to the carbon, but also the barium. So these are not related to neutron star merger and whatever. And then there is also one barium poor star, which I will discuss later. So pair instability supernovae are predicted to be a common fate for the very massive star, for the very first generation of stars. And they pollute the interstellar medium with a precise yields. Here I'm showing the yields from Takahashi 18. And you can see that some yields are that does not depend much on the Pisney mass. And Lucy in 2022, they did a similar work, trying to find if their bulge star were like polluted by Pisney, and they did find that 2 stars were calcium over magnesium compatible with Pisney yields, while the aluminum was too high. Can we do the same? Well, in Graces, we don't have aluminum, but we can use sodium. And here I'm showing the sodium over magnesium versus calcium over magnesium. And similarly to Lucy, we did find 3 stars with a calcium over magnesium compatible with Pisney, but the sodium is too high. And then there is another star which is totally the opposite, a good sodium over magnesium, while it's too low in calcium over magnesium. So maybe the Pisney alone is not enough to describe this chemistry. And the majority of the star again look like the halo, since the halo star should be picked at calcium over magnesium of 0, since we have a equal contribution of calcium and magnesium, since they are both alpha elements. And then we also discuss about a possible connection with the 2nd generation stars from globular cluster. So it has been found in the past that that there is the presence of many nitrogen-rich stars in the bulge, and they occupy the same chemical region of the 2nd generation stars from globular cluster. And it has been shown and estimated that maybe the bulge is, let's say, produced by ancient and dissolved globular cluster that can constitute up to the 25% of the inner galaxy mass. So again, we want to see if we can find similar stars here. So this has already been done also from Lucy in 2022, looking at the aluminum versus magnesium, in which the high aluminum can be linked to second generation stars, already shown here by Pancino 2017. And if you can see in this box, there is this is the region of second generation stars, which you will have high aluminum and relatively low magnesium. Can we do the same? Well, we don't have, again, aluminum, but neither nitrogen. So what I propose here is to use sodium over magnesium instead of aluminum over iron. And here I'm putting my sample and also the Pancino sample color-coded by first and second generation star. And the second generation star is selected from the aluminum, from this region here. And you can see that in this part here is mainly populated by second generation stars. So probably we have 2 or 3 stars compatible with the second generation stars, while all the other looks like, let's say, first generation or the halo. And but what we can say about these stars, so one is carbon enhanced and also barium rich. So we said that likely to be polluted by an AGB companion, so probably sodium is also enriched too. And so this star should lie down. We don't know how much sodium is produced by AGB at the moment, but however, it would be very rare to find such a star in a globular cluster since the rarity of binarities in globular cluster. So this will be extremely rare if it's both carbon enhanced and globular cluster. And then the other one has a metallicity of -3.2. And then if the globular cluster nature is confirmed, that will challenge again the metallicity floor, as shown by Nicolas in a previous talk. And then we also do a comparison with extragalactic globular clusters. So it has been shown that extragalactic globular cluster has a low magnesium over alpha, so only the magnesium is poor, and which produce a negative value here. And our 4 star here lie exactly in the extragalactic region. So maybe they have been accreted very early from extragalactic globular cluster. And then the last slide, the 2 last slides. There is also an interesting planar star, which has a very different apocenter from the other, low in sodium, calcium over magnesium, and barium. So probably it has been accreted from a dwarf galaxies. And dwarf galaxies that has been polluted by one or very few low mass supernovae, the so-called one-shot model. And yeah, this can explain these chemical properties. And then we did find other stars in the literature with similar chemistry, but also similar kinematical properties with high eccentricity, pericenter in the bulge, with a planary-ish orbits. And we can conclude with this question, maybe are they accreted from the same structure? It's still premature, but well, in the past we did find a large population of very metal poor star with high eccentricity in planar orbits without chemistry. So we only had kinematics. So what I'm doing now is also doing an ongoing spectroscopic follow-up with espadons to see if we can see the same chemistry as the previous star that I showed before, and maybe see you again at the next meeting with these new espadons data. And I leave here the take-home messages. So yeah.
Thank you very much.
Yeah.